There's a single irrational number woven so deeply into the fabric of reality that it connects the architecture of the universe to pure discrete mathematics. Well, it's not pi, it's not Euler's number, it's the golden ratio, approximately 1.618, the center of what we're going to be talking about today. We see the golden ratio everywhere, from art to nature and to inside of general math. But before we actually get into how this fits into the Fibonacci sequence, let's think about generally how we define the golden ratio and why it's 1.618. Most people think that the reason the golden ratio is hidden everywhere is a design rule or just a universal quirk, but we're going to talk about the pure mathematics behind why it's everywhere. Well, let's actually dive into what the golden ratio is defined as. Geometry gives us the simplest proof for this. So if we have a line, we cut it into two segments, a longer line A and a shorter side B, and the entire line we'll call C. If the ratio from A to B is equal to the ratio of C to A, basically meaning the ratio of the longer side to the shorter side is equal to the ratio of the entire line to the longer side, that is where we get the golden ratio, also known as phi. We can also write this algebraically. A over A plus B over A equals A over B. You know why this works? The reason why this works is because C is just A plus B, and the ratio C to A is represented as C over A, which is just A plus B over A, and well, the ratio A to B is also just A over B. And that is just the golden ratio in the simplest terms. Now, how do we turn this geometric concept of if the ratio between the longer side and the short side be equaling the ratio between the entire line to the bigger line? How do we translate this into 1.618 or phi? Well, first of all, we can just say that let's just manipulate this. So A plus B over A is the same as 1 plus B over A, because it's we could also just write this as A over A plus B over A, and that is equal to A over B. Now let's set A over B to be phi. 1 plus B over A equals phi. Now, how exactly could we translate? Now, what can we do with this to get a simpler quadratic or something like that? Well, what we can actually do is we can realize that B over A and B over A is just inverted A over B. So we have 1 plus 1 over phi equals phi. Now, what we can do to just get rid of this fraction is kind of annoying. We can just make this into, we can just multiply both sides by phi. So now we get phi plus 1 equals phi squared. Now we can rearrange this to get phi squared plus subtract 1 equals 0. Now that we have this quadratic, what to do next? What we do next is we simply just run this through the quadratic formula. By the way, this is 0, and we got 1 plus the square root of 5 over 2, which actually equals 1.618. Now we know that square root of 5 is irrational, so we know that this is definitely irrational. And well, now we know that phi equals 1 plus the square root of 5 over 2, which approximately equals 1.618. And that is how we can turn this geometric concept into this number. Okay, I kind of forgot to add this. Very sorry. Here's one thing. We are only including when we were talking about the quadratic formula and 1 plus the square root of 5 over 2. The reason why we didn't do plus minus is because we're not going to have a negative distance for a line. so we're only including the positive. Now, how does the golden ratio fit into the Fibonacci sequence? Well, the Fibonacci sequence is defined as f sub n equals f sub n subtract 1 plus f sub n subtract 2. Now, let's just change f sub n. Let's call it let's say it equals r to the n as well. Okay. Now let's just substitute this. Let's get r to the n equals r to the n subtract 1 plus r to the n subtract 2. Next, let's divide this by r to the n subtract 2. So now with this, we actually get r squared equals r plus 1, which is also equal to r squared subtract r subtract 1. Doesn't that look familiar? Phi squared subtract phi subtract 1, both equaling 1 plus square root of 5 over 2. Now the thing is, for this specific equation, it is 1 plus minus square root of 5 over 2. Now that is why it's literally fundamentally within the Fibonacci sequence. This is plus minus over here, which means that there are two solutions. There's the golden ratio, which would be 1 plus the square root of 5 over 2, and we also have which is equal to 1 subtract the square root of 5 over 2, which you might think is completely different because it starts with, which is actually equal to negative 0.6, but it is actually also just equal to 1 over 5. So that's quite cool. They are very well, they're not completely different, but there is a negative root. The thing is, for us to actually get the Fibonacci sequence, we need both the this root and this root. So the actual Fibonacci sequence isn't just f sub n equals the golden ratio or something. Because if we actually just put the golden ratio to any n, then it would never be a whole number. So imagine this 0.6 going on forever. Imagine it as sort of the cleanup crew, the thing that says, let's make this a whole number. So first of all, the actual Fibonacci sequence is f sub n equals a phi squared to the n, f phi to the n plus subtract b to the n, and then you get Bennet's theorem, which literally just says that f to the n sub n equals the golden ratio to the n subtract over 2. Now, this obviously is a very, very similar to this. Literally has the golden ratio stated twice. This isn't the golden ratio, but it's very similar. It is completely intertwined with the golden ratio, this constant. So that we've basically found a new way of expressing the Fibonacci sequence. Now, this is obviously much less efficient than just saying this, but just saying the normal definition. But it's a cool way to represent the Fibonacci sequence. Now, we have just proved this, that the DNA of the Fibonacci sequence is the golden ratio. But how do we prove that the ratio between two Fibonacci numbers, as we get higher and higher Fibonacci numbers, approaches the golden ratio? First of all, you can see the first term is 1 over 1, which equals 1, then it's the next it's 2, then it's 1.5, then it's 1.6, 1.6, then it's 1.60, and you can see that it does seem to be approaching a number. We can't exactly pinpoint it yet, so we're going to use limits to try and actually find the reason why. As the nth term of the Fibonacci sequence approaches infinity, if we find the ratio between the consecutive a number and its consecutive number, it approaches the golden ratio. Okay, so let's actually prove the ratio using limits. So first, to find the ratio between one Fibonacci number and the next, we can simply use this f sub n plus 1 over f sub n, and it's the limit as n approaches infinity. Next, let's apply Benet's formula into f sub n plus 1 and f sub n. So it would be phi to the n plus 1 subtract psi to the n subtract 1 over the square root of phi over phi to the n subtract psi to the n over square root of 5. Now, these two square root of 5s actually cancel out. Thus, we have the limit as n approaches infinity of phi to the n plus 1 subtract psi to the n plus 1 over phi to the n subtract psi to the n. Now, what happens to psi? Let's think about psi. What happens to psi as we raise it to massive number, raise it to the power of massive numbers, such as infinity? Well, any fraction, when you multiply it by itself, it gets smaller and smaller. So eventually, psi to the infinity equals 0. So what we know is that psi actually has no influence on the equation. What do we get with that? We get phi to the n subtract 1 over phi to the n. What does that equal? Boom, and that's it. So, in this video, we've done a lot. Thank you so much for watching. Please do subscribe if you managed to get to the end. I know this is a very long video, so if you actually managed to get to the end, thank you so much.